Hi folks, welcome back. This is the fifth and final lecture of this Kinetics lecture series, where we're going to take a look at collision theory and what it tells us about the effect that reaction energetics and temperature, this kind of battle over the energy available and the energy that is necessary, can have on the rate of a chemical reaction. And so to do that, we need to take a brief look at collision theory first. Remember that for a chemical reaction to occur, we generally consider that two or more molecules must first collide with one another. And so we kind of view this as, for instance, XY, which is going to be a diatomic molecule here, and Z, a single atom, banging into one another accordingly. And when they do this, we assume that a bond is going to break, few new ones might form, and what we wind up with are the products. And so in this situation, let's say we broke the XY bond, we form one between Y and Z, and as they go off their separate ways, we now have two new substances with different properties. And so in this particular model reaction, we imagine that there are a couple of things that are necessary for a collision to be successful. It's not just that you need them to hit each other, this other stuff has to happen. First and foremost, we know from our experience in Chapter 6 that breaking bonds costs us energy. And so we can feel pretty confident that to do this, the first condition that must be fulfilled is that the molecules have to collide with enough energy. If I just let them kind of drift in and bang off of one another without a whole lot of verve, I'm not going to break anything. And if I don't break that XY interaction, there's no reason for Y to want to form a bond with Z. It's already satisfied. Additionally, no matter how hard I happen to smack them into each other, if they don't hit at the right angle, I'm never going to form the thing I want. If I let the XY molecule come in backwards so that the X atom hits Z, like this, I can ram them at each other and it won't make any difference. They still don't end up forming the new molecule. And so even if I destabilize the first bond, I don't have the ability to form the YZ bond the way I'm expecting. Now, I skipped over it a moment ago, but the first thing, the amount of energy that's necessary, is referred to as the activation energy of the reaction. And when we talk about the molecules colliding in the right orientation, you're going to see a factor for that in a moment as well. We call it the steric factor. Pretty much anything that involves the 3D nature of how molecules and atoms and electrons, for that matter, interact with each other gets this word steric. And so we'll use P as a variable for that. Notice up at the top, collision frequency is going to be denoted with a Z instead. So to get at that minimum energy that's going to be necessary, we're going to take a look at the reaction energy dynamics that are taking place as this reaction occurs. Remembering that stable molecules have lower energy in general than the atoms that make them up. That's why they form bonds in the first place. We know that when you form a set of chemical bonds, you generally release energy. When you break chemical bonds, you demand energy in order for that to happen. You're going to use it up. Now, examining this pair of reaction energy diagrams that have nothing on them right now, we know that there are two ways this can work out in the wash. One possibility is that the reaction is going to lose energy because the bonds it forms will release more than are being consumed in the first place. That would be something like, for instance, lighting a fire. You're going to see this sort of thing happen. Whereas for other reactions, you might go the other way. You might end up using up more energy than you ever get back. You could consider this like a bad investment in a pyramid scheme of some sort, where you put in the money, you don't get anything back. It's a bad deal. As far as the energy is concerned, that is generally how the reaction system feels in this situation. But I want you to notice something. We know that nature loves reactions that use up energy. However, if I look over here at the reactants and the products, we've already kind of seen it from collision theory a moment ago. There doesn't seem to be anything that should stop this from happening. The way we've drawn the diagram looks like a ball bearing could be sitting on the reactant line and just roll off onto the products. That reactions like this should just be spontaneous and happening all the time. Well, it's good news for us that it's not. If you think about us sitting in a classroom together at a bunch of wooden desks, we have all the ingredients for a fire in there. We have wood, we have oxygen in the air. And yet, thankfully, we are not sitting inside that room just bursting into flames every time we try to have class. And the reason for that is that, as we've seen, something has to happen to get me from reactants to products. And that's even true of the elementary steps that we examined in the last video. We saw examples where you might make some high-energy species, but even those reactions need to go through a process to happen themselves. And that process is the sort of thing that humans are very, very good at modeling, because human beings in general tend to be fantastic at thinking about what the intermediate steps should look like between starting and stopping. So for example, if I'm beginning with X, Y, and Z separate, and then I end up with X on its own and Y and Z bound together, you can very easily ask yourself, what should it look like in between? And there are two things I can come up with that make a decent bit of sense. One is that I'm going to break this bond before anything else happens, and so my intermediate step looks like this. And then eventually Y and Z find each other, and they go here. So this would be my transition state. Another possibility, and admittedly a more likely one in most chemical reactions, is that all of this might happen at once, so that I have some half-formed and half-broken bonds at some moment, and I end up with this sort of transition state where all three atoms are together. Now, everything I'm about to say for this is also true here, but it's a lot easier to see it for this kind of transition state. In this one, I can see very clearly that getting from reactants to transition state meant I broke a chemical bond. That means this transition state must be a higher energy than where I started. By the same token, getting from here to there, to the product side of things, involved the formation of a chemical bond. Therefore, this would have to release energy. So the transition state must be higher in energy also than the products are. And what that's going to mean, coming back to our diagrams from a moment ago on the PowerPoint, is that when I draw in the full process and the transition state itself here with the green asterisk, I wind up with a hill to climb. I've got to go up in energy before I come down, and that is regardless of whether the eventual landing spot is going to be lower or higher than where I started. I always have to go up first. And so it is this amount of energy necessary to put in that we term the activation energy. And you can think of it in some ways as another speed bump. It's the amount of energy that's necessary here for us to get over the top of this. Now, the faster molecules are moving, the more likely they are to have that much energy. And the lower that hill is, the more likely they are to also have the requisite energy. If you don't require quite so much, I don't know if any of you are musicians, but I am. When I try to get friends to come to a concert, the cheaper it is, the more people show up. That's kind of how activation energy is going to work as well. And so that's what we're going to see here. Higher activation energy is going to mean fewer molecular collisions have enough energy to cause the reaction. That's going to result in a slower rate. And of course, the opposite, everything I was saying a moment ago, also very, very true. Now, to get a grip on how many molecules will have enough energy to do this, we need to take a quick peek at the Boltzmann distribution. This is something that you may have seen in chapter 11 of your book. You don't need to worry about this in any real mathematical sense, but what you guys observed in chapter 11 was that, among other things, when I raise the temperature, the molecular speed not only gets higher on average, but the entire distribution widens and shifts to higher molecular speed. And so what you see shown here is essentially what that distribution looks like for 0 Celsius and 100 Celsius, I believe, for water molecules. So this is defined by their temperature. No matter what I have, if I'm looking at a specific molecule at a specific temperature, I can draw this diagram. Now, one useful bit of statistical mechanics and integration that's been done over the years allows us to understand how many molecules, or I should say what fraction of molecules in this distribution have at least a particular energy. So if I put a borderline at a certain spot, like say there, I can see that at that speed, my energy would be 2e divided by m, and then the square root of that. That's just me solving 1/2 mv squared for v. I know that if I take that amount of energy and I plug it in to this expression, e to the minus negative energy over RT, that is the ideal gas constant, by the way, and the temperature in kelvins, that will tell me what fraction of my molecules have at least that much energy. Not that have exactly that much energy, but have that or more. That Boltzmann factor right here becomes extremely important because what it essentially shows us is what effect I will have if I vary the activation energy or the temperature on the fraction of successful collisions. And so with that bit of knowledge, we can really start to model this a little bit better. We knew already that the reaction rate depended on collision frequency. More times they bang into each other, the more frequently I actually get a reaction. The more chances I get, basically the more lottery tickets I buy, the more likely I am to win the jackpot. But it doesn't just depend on them being frequent, it also depends on them being successful. And so we just saw that collision success is broken down into two things: the fraction that collide in the right orientation, and the fraction that collide with enough energy to actually undergo the reaction. And we're going to replace in that Boltzmann factor right now E sub A, the activation energy, for just the generic E that I had a moment ago. And so that gives us an equation that looks like this. Essentially, what it tells me is that the K that we've been talking about this whole time is really an agglomeration of all these factors. How often do they hit? How often is that in the right orientation? And how many of those collisions have enough energy? And essentially, you're just taking numbers that are smaller than 1 and attaching them to the collision frequency to get to the amount of successful collisions. And in general, what happens with the Arrhenius equation, which is what we're essentially deriving here, is that Z and P get lumped into one constant, A, that's known as the frequency factor. And it essentially accounts for collision frequency and this fraction colliding in the right orientation. This equation is exceedingly useful, frequently in the same way that the rate law was back when we were trying to figure out the exponents that went into it. What this allows us to do frequently is take two different sets of conditions and determine what the activation energy might be. Or, if we know the activation energy, figure out what effect temperature might have on something like this. And so we're going to try out a problem here, and I'll give you a moment to read it. We're going to be dealing with a first-order reaction that has these two rate constants. Notice again, the rate constant units just simply time to the -1. That's what we expect for a first-order reaction. And so we've been provided the rate constant at two different temperatures, 0 and 20 degrees Celsius, and what we're going to try to do is find the activation energy. Okay, so based on the numbers that were provided to us, what we can do is take this original Arrhenius equation and simply plug in the numbers we have, and like we did back when we were coming up with rate laws in the first place, do it for the two sets of conditions. So in other words, I start off with this K of 4.6 times 10 to the -2 inverse seconds being equal to A times e to the minus E sub A over R times T. And in this case, the temperature for this one is 0 Celsius. We're going to write that as 273 Kelvin because we know that's what we're going to need eventually. That's the unit that is in the ideal gas constant. And now we can do the same thing. We can set up the same equation for the result down here at 20 degrees Celsius. And notice that the K is a little bit bigger, which makes some sense because the temperature is a little bit higher. I should have more energy to go around, and as a result, be able to have the reaction go a little bit faster. Now, what might alarm folks at first when you write out the first equation is the fact that you've got two variables. But now that we've got two equations, we no longer do. We can actually make some sense of this, and if we want to solve for A, we have that option eventually. But the thing we're going to look for here first is the activation energy because that's what I asked you for. And so we'll do the same thing. We're going to take this equation and divide them by each other. Recognizing that if I do that, if these two were equal to begin with, then their quotients should also be equal to each other. And so what that's going to mean now is that I have a value of 0.57 over here. That actually cancels out. The other thing that cancels is A. Now, in this case, I've got e to something over e to something else. And so exponent rules tell me that I'm just going to take this and subtract that, and that can be the big exponent. So it's E sub A over R times 273 kelvins minus a negative E sub A over R times 293 kelvins. Now that we have all of this, we want to pull this all down. Because right now this is a bit annoying to deal with. I don't like having to write that tiny in the first place. If I want to undo this exponential, I'm just going to take the natural log of both sides. And of course that's going to pull that all down. Natural log of my original number here turns out to be negative 0.57, which is an interesting coincidence. Just so we're clear, I didn't flip the sign. That is actually its natural log. And then all of this is now going to be E sub A over R times 293 kelvins, which is positive over here, minus E sub A over R times 273 kelvins. Notice that minus a minus is a plus. That one's still negative. That's what I wind up with. And from here, what I can do is start basically just solving my way through the algebra. And so what I should see here is that I can take E sub A and actually remove it from this, along with R, which is 8.3145 joules per mole Kelvin. And what I now have is 1 over 293 Kelvin minus 1 over 273 kelvins. All of that equal to minus 0.57. I can multiply both sides by R, and I can solve for that. And so if I multiply my left side by R, I'm going to wind up with negative 4.704 equals EA times, and now 1 over 293 minus 1 over 273 is going to give me a very small number of a negative 0.000250. And that's in kelvins to the minus 1. Note that this number right here, since I multiplied by all that, would be joules per mole Kelvin, and that's also a big deal to recognize. When I divide this through by both sides, the kelvins are going to go away. I'm going to get something in joules per mole. And so I'll move this up a little bit so we can see what we're doing. But the end result of this here is going to be 18,800 joules per mole equals E sub A when I divide both sides by that. So in other words, roughly 19 kilojoules per mole. And once you have that number, you can do more interesting things. Notice that at the end of the day, what was interesting to us here was actually the ratio between those two. It's a very nice thing to know, because it means that if I gave you a problem a little different, something where I'm not actually asking you about specific K values, but instead said something like, at what temperature is the reaction 20 times faster than it would be at 40 degrees Celsius, you'd be able to answer that, because the ratio is really all you need right here. I've given you a temperature, you have the activation energy, have at it. And so that will be the next question that is actually on the Canvas quiz, I believe the last one that I have, which is to solve this problem. Determine at what temperature will this reaction be 20 times faster than it is at 40 degrees Celsius. Have fun. Now, we've already seen the ways that reaction rates can depend on all these things mathematically, on orientation, sufficient energy, and available energy. If you're an industrialist, something you might want to do is find a way to do a reaction quickly, right? You know, time, sitting there in the bottom of your reaction rate, we all know the very standard equation, time equals money. Well, so does K. Higher K means more money more quickly. Now, one way you can do that is to raise the temperature of your reaction. Of course, that's got its own issue, because that's going to cost you on your heating bill. And so that's not going to help you out with making the money. You want something that can make your collisions more successful, even if the temperature doesn't change. Namely, you'd like something that would enforce proper positioning. Remember that a bunch of your collisions don't succeed because they don't hit the right way. Additionally, you'd love a path with a lower activation energy. Some sort of path that removes this barrier so that more of your collisions have sufficient energy, because having sufficient energy isn't as hard anymore. Well, substances that meet those latter two conditions are things that speed up reactions in general. And if they're not consumed themselves, we have a name for them. We call them catalysts. And in fact, when they're in the human body, or in any sort of living organism for that matter, we call them enzymes. And in theory, here's essentially what they're doing. You're providing a path with a lower activation energy. And I'm going to give you a picture of how that might happen with a particular substance in just a moment. But here what you can observe is that if I've got a lower activation energy and this barrier isn't as high anymore, what that's going to mean to the Boltzmann distribution, recall, is that there's a larger chunk of this graph containing molecules capable of undergoing the reaction. If my uncatalyzed pathway requires me to have at least that much speed, then I would expect that my catalyzed pathway might only need the molecules to be moving that fast. And as a result, instead of getting just that little tiny tail at the end worth of molecules capable of reacting, I'm now getting everything upstream where I have a lot more molecules, a lot more of them moving at those slightly lower speeds. And so this will make my collisions more likely to succeed just simply by lowering the barrier necessary for one to be successful. And here's a quick example of how that might work. In terms of enforcing the proper orientation, this is an enzyme called chymotrypsin that is responsible for breaking down proteins in your bloodstream. Also used very frequently in actual biochemistry for, again, that exact purpose, just chopping up proteins into amino acids. Now, the left side of our substrate, this big six-membered carbon ring and the CH2 and the CH, all of that is what we would term hydrophobic. It's very nonpolar. It tends to shove water away from it. And so one of the neat things about this particular protease is that it breaks down proteins at a specific spot, at a specific amino acid, because it's got a bonding chamber that will accommodate this particular amino acid. This is the side chain for phenylalanine. Now, the other thing it does is it stabilizes the presence of this CON moiety, this portion of the substrate where the actual chemical reaction is going to happen, where we're going to break the C to N bond. And what it does here, essentially, is it attracts the carbon, which has a slight positive charge because it's bound to an N and an O, and those guys are electrons hogging bullies. And it stabilizes it by bringing a serine side chain with its oxygen nearby. It does the same thing on the other side with these NHs that are from the actual backbone of the protein itself. Those H's are forming hydrogen bonding attractions with the oxygen in that double bond. The other thing they can help out with is that along with attracting the oxygen up there, they'll even attract the electrons a little bit. And so if the transition state involves electrons moving in that direction, perhaps from the N to the C up through the O, that is going to be a much, much easier thing to make happen if you start the process with some positive charge up where you want the electrons to move and some negative charge where you want to push the electrons away. And so all of that is going to allow this enzyme to lower the activation energy and provide a pathway that works a lot better. I encourage you to ask me any questions you might have via email. I won't be getting to them necessarily until about the 2 weeks before class gets rolling. I'm going to be traveling until the 11th of January. But after that, I'll be on my email looking for questions from you guys. Try out the quiz on Canvas. I'm going to make that website available as well starting on the new year. And have at it. Enjoy yourselves. I look forward to working with you and building on some of your understanding of kinetics on our first day of class on January 28th. Take care.